Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 27th lecture on robot control. All right, so let's get started with a video. Now, control is all about moving my robot in the real world. You can imagine your arm and think about, how do I apply torques to my joints to move this arm to a desired position or follow a reference trajectory? Well, that's what we're seeing in this video. Here I've got a rehabilitation exoskeleton, and we're using control to make the arms move along a cyclical pattern. So part of control is following these reference trajectories, but another part of control is stability, making sure that when I move in the real world, I can deal with disturbances. And here we have two different designers that are applying forces and torques to this robot arm. They're applying these external disturbances. I like this video because it highlights the stability of this controller. No matter what the users do, how they interact with this robot arm, it still goes back to safely following its reference trajectory. So here's a great example of a controller in action, and that's what we're going to be talking about in today's lecture. We're just going to briefly recap what we learned about robot control, and then I'll give you some more information on how you implement a robot controller. I think this is a rather fun lecture because it leads into a practice set where you can test a lot of these concepts for yourself and actually visualize a robot and then pick different control gains to make that robot move around in space. Okay, so let's get started with recapping control. So given the dynamics that we found for a robot arm, how do we control a robot with different joint torques tau in order to move from its current position to some desired position? So again, what we're thinking about is, I know I've got all these different motors along the robot arm, and I want to figure out, how do I pick the torques or the forces for those motors to make my robot move the way I want it to move? Well, there are two main approaches. The first approach we discussed is something called independent joint control. And what we did is we took this entire robot arm and we separated it out into different joints and links. And then we developed one controller per link. So I'd have one controller for the first joint, another controller for the second joint, and so on. So this takes my overall multi-body system and breaks it down into a variety of different single input, single output controllers. So again, independent joint control, it's a very common way to control robot arms, and it separates the overall robot into a variety of different joints and links. And then when you do that, you can apply linear control techniques. On the left, I've got a quick example. So here I've got my first joint of my robot. Let's say it's with position theta 1. And I can take this prismatic joint and I could actually just model it as something like a mass damper. All right, well, when I look at it in that perspective, this mass damper, that's something we've seen before in linear control, and I understand what to do here. I can just design some sort of PID controller in order to make this mass damper move to the desired position. Now, because we're using kind of classical linear control techniques, we often perform our analysis in the Laplace domain, and we use things like the characteristic equation. So here's some examples of the approach you might use if you're using independent joint control. The other common approach is multivariable control. And here I've just developed one controller for the entire robot arm. This controller is going to take in vectors of my desired joint position and my actual joint position, and then it's going to output a vector of the commanded joint torques. So again, multivariable control, that's the second common approach. And here we're developing one control law for the entire robot arm. But because this is a multi-body system with multiple inputs, multiple outputs, and nonlinear dynamics, we need to use different techniques in order to develop and analyze these controllers. And that led us to something called Lyapunov stability analysis. Now, I'd point out that all of our analysis here was performed in the time domain. The basic idea for this analysis was, we thought about the energy contained in our system, and we wanted to show that when we apply our controller, the amount of energy in the system decreases over time until I come to rest at an equilibrium position. Okay, so those are the two main control approaches that we discussed, and what I want to show you today is how you can go about implementing one of those controllers in practice. So let's get started, and I want to focus a little bit more on the latter approach, the multivariable robot controller, but the same steps can be used for independent joint control as well. So to get started, I'm going to initialize my robot with some gains. These are going to be my proportional and derivative gains. Again, for a multivariable controller, these are going to be symmetric positive definite matrices of my choice. If you wanted to go with independent joint control, this would just be a list of all the gains for the different joints along your robot. So I'm going to pick my choices for KP and KD, and we'll talk a little bit more about tuning those later in the lecture. I also want to pick some desired position, because again, the whole point of control is to take my robot and move it to that desired position. So here theta D, that's going to be my desired joint position for my entire robot arm. I'm also going to want to have my gravity vector g, and this is going to be especially important for multivariable control. The idea is that this will cancel out any steady state errors caused by the effect of gravity. So if gravity is pulling my system down, I want to include this gravity vector so I can cancel that effect out. And of course, the more accurate your estimate of the gravity vector, the better this is going to perform. So if you have some sort of inaccurate model, you'll have more steady state error in your controller. Okay, so I've got all these things set up. Now I can get into my main loop. And so while my robot is working, these are going to be my main steps. The first thing I want to do is I want to measure my joint position. And I can use this, do this using something like the encoders along each of the different joints of my robot arm. So I measure my joint position, and then I also want to measure my joint velocity. Now here, I often don't have sensors that directly measure joint velocity. And so what we do instead is I take my joint position and I perform numerical differentiation in order to estimate my joint velocity. It comes out to a pretty accurate estimate, and so I can work with this. Now that I have my joint position and my joint velocity at the current point in time, I can plug them into my control equation. And here for my multivariable controller, I'm using what we derived together. So I'll have my gains for Kp and Kd, I'll have my position error, my velocity, and then my gravity vector. And just plugging all these in, I'll get an output of a vector, an n/1 vector of joint torques. And I just take those torques and I tell my motors, hey, do this. So I'm getting those commands and sending them to the motors. Now this whole loop will be running very quickly. Ideally, I'd run this to something like 1,000 times per second, because all I'm doing is I'm just checking my encoders. All right, where's my robot? Got my position, got my velocity. I quickly compute the desired torques, and then I send those torques to the motors and ask them to deliver those torques on my actual robotic system. So this loop can run quite quickly on a computer or a microcontroller, sending its signals in real time to the robot, and the robot executes these torque commands on its actual robot arm. So this is what the implementation looks like for my controller. Now, here's a visualization of me using that implementation on a simulated robot. Now, I'm going to start off on the left here, and this is my video. Now, this is a 2-link robot arm that you will also get a chance to try out in the practice set. My first revolute joint is right here, and my second revolute joint is right here. So it's a robot that's moving in a plane with 2 revolute joints, and then here's my end effector. Again, you can think about this as an XY plane where the Z-axis is coming out of the screen towards you. And then in yellow, I've marked my desired joint position. So I'd like my robot to have a joint value of 0 degrees here, and then pi/2 here. So 0 pi/2, and that's going to get the end effector to move to this yellow position. So this is my desired position. Again, you can pick that to be whatever you like. This is just the desired position I want my robot to reach. And then here are my gain matrices. Again, I can tune these. I just want to make sure they're symmetric and positive definite matrices, and that's what I have right here. So if I look at my controller on the left, you can see the robot is moving toward the desired position, but it doesn't actually get there within my allotted time limit. So maybe I could try tuning my gains. One intuitive idea is maybe I could just increase my gains and perhaps I'll get some better performance. And that's exactly what I'm going to do. I'm going to take my proportional gains and crank them up so it's 100 along the diagonal. Previously it was 10 along the diagonal. And now you can see a video of the robot quickly snapping to that desired joint position. It's not perfect. You can kind of see that it's oscillating. It goes a little bit beyond the desired joint position, then goes backwards. I'd call this an oscillation. So it's not perfect, and you can actually improve this by tuning the gains yourself as part of the practice set, but it's better than what we saw before. So again, this is me implementing control in practice where I've got my dynamical system, I've got my robot arm. If I did nothing, this, as you've seen in previous lectures, this robot would just swing back and forth until it comes to rest along the vertical axis. But here, I'm applying my controller to get my robot to move to that desired joint position. Okay, so a big question you might have is, how do I go about tuning these control gains? Now, this is a bit of the art and the science of control. First things first, always make sure that your gains are stable. Now, if you're using independent joint control, you'll be thinking about something like the Routh-Horowitz condition in order to show that these gains are stable. If you're working with multivariable control, you just want to show that these have symmetric positive definite matrices, kind of following the Lyapunov stability analysis we had in the previous video. But yeah, first things first, always make sure you've got stable control gains. Now, once you've checked for stability, you can start tuning these gains, and in general, increasing your control gains will likely lead to better performance. The patterns you might see is if your robot is taking a long time to get to the desired position, that might be a situation where you want to increase Kp, your proportional gains. And if the robot is oscillating around the desired position, like what we just saw, that might be a time when you want to increase your derivative gains, Kd. So you're increasing your gains, increase proportional based off of how long it takes to get there, and KD based on the oscillations. So, all right, if increasing my gains generally increases performance, can I just crank them up towards infinity? Short answer, no. A bit of a longer answer, the larger your control gains, the more torque you're demanding from your motors, and the faster you're expecting your robot to move. In practice, your physical robot may not be able to deliver these incredibly high joint torques, and it may not be able to move as quickly as you're commanding it to move. And this can actually damage your physical robotic system. So it's better to start off with smaller gains and to gradually increase them, and recognize that there will be an upper limit beyond which you cannot increase your performance. And in fact, you're just demanding what your robot cannot deliver. All right, so that's some general guidance for how you might implement a robot controller. And the fun part about this lecture is I've actually set it up so you can try these different concepts yourself. I encourage you to go to the practice set, download the code that goes with that practice set, and try it out. On the first page, you can see the questions, and on the following pages, you can see the answers for these different questions of tuning your robot's control gains and seeing how it performs. And with this, we've kind of wrapped up our lectures on control. So we know how to make our robot move to a desired position. And now I want to think about maybe learning more complex behavior. So instead of just going to a desired position, how can I make my robot learn and perform more complex actions in the real world? And we'll start talking about learning in the next lecture. I look forward to seeing you there.